So welcome back. So what we have now is no pen again. So I seem to be having a lot of problems with my pens. I did something to it. Sorry, I need to do that. Maybe that's going to help me. Let's just put you on pause. Zoom recording. So welcome. We had to fix our pen and everything, but so okay. We know that when light goes from one medium to another, one refractive index to another, then there's a effect. It slows down the light. So light goes slower when it goes through glass than it does when it goes through air. And that leads to some bending effects. And I didn't actually do an example with this. Let's go back here. So here's the instant ray. And there always is a little bit of reflection. Let's ignore that for the minute. Here's the refracted ray. And that has turned towards the surface normal. And that's because this is something like air, and that's something like water. So I'm going from a low n is low, to n is high. When I go from a low end to a high end, I am refracted towards the surface normal. If I was to go from a low n to a lower n, I would refract away from the surface normal. So I've got to remember which way around this is. And so the best way, I think, to do that is to remember a specific example and then use that as your guide. So the specific example that I use is air and water. And when the light goes from the air to the water, the light is bent towards the surface normal. And I can show that, I can remind myself of that by saying, here's the surface of the water, and here's the swimming pool. And here's a rock on the bottom of the swimming pool. And if I stand at the side, light from that rock the light that enters my eye will have that kind of path. Because light, this is the low refractive index side, and this is the high refractive index side. And if the light was going from the low to the high, it would bend towards the surface normal. If it's going from the high to the low, it bends away from the surface normal. And this is why we always think that water is shallower than it is. Because there's the direction of the light that is carrying the information of the brick. And I'm used to light traveling in straight lines. So I assume that the water is only that deep, when in fact the water is that deep. That's why water appears shallower than it really is. So I remember that example, and I can say this is n is low, n is high. And if you ask me any questions about that, I can just refer back to this memory. And I can say, well, now you're doing the opposite, or now you're doing the same, or whatever. But if you just try and remember it cold, I think you get confused. Okay? So that's one thing. And then let's use this. So let's use this. Let's go to here. And let's do a typical example. So in this typical example, we have diamond. N equals 2.4. And let's have oil. Oh, let's have air. No, let's have oil. N equals 1.5. And I have a situation where my angle of incidence is 30 degrees. And I want to know my angle of refraction. Angle of refraction. So I go, well, n1 sine theta 1 is equal to n2 sine theta 2. Well, this is going to be, let's call this the 1 side and that the 2 side. So 1.5 sine 30 is equal to 2.4 sine theta 2. So sine theta 2 is equal to 1.5 sine 30 over 2.4.
So theta equal.
Yeah, so theta is equal to sine to the minus 1, 1.5 sine 30 over 2.4. So theta equals, and we're going to go and we're going to say 1.5 times sine 30 divided by 2.4, and then I'm going to go second sine second answer. I'm getting 18.2 degrees. So that angle there is only 18.2 degrees, whereas the angle coming in was 30 degrees. That's a typical example. So, okay, let's take a shape where we have a prism. So it's a triangle of glass. So I get refraction at the first interface, and my angle of incidence will be bigger than my angle of refraction, because I'm going from a low medium to a high medium, low N to high N. Glass is about 1.5, 1.6. Air is 1. Think of air as just being like vacuum. So that changes the direction of the object, of the ray. And then as we're leaving, again we have another, and I have my angle of incidence, and I have my angle of refraction, and now I'm going from a high medium to a low N medium, so I bend away from the interface. So whichever way I do it, I get this kind of shape. And if you ever saw, what is it, Dark Side of the Moon by Pink Floyd, you know, you've seen this kind of thing. We define the angle of deviation as being the angle between where the ray of light would have gone if the prism had not been there, and where the ray of light did go. So the interesting thing is the angle of deviation is that angle there, and it is not obvious, you know, it's inside the object. You can't just measure it, kind of like. So that's the angle of deviation, and I want you to know that angle, know what it is, know where it is, and we're going to practice how to find it. And then the second part to this is a recognition that I've been, like we talk about models, simple models for simple situations, and then more complicated models for more complicated situations. I've been talking about diamond having a refractive index of 2.4, when in fact diamond has a refractive index which is frequency dependent. It's not very much frequency dependent. It tends to be pretty constant, but it's not perfectly constant. And I've not got the example for diamond here, but I have crown glass, and I have acrylic, and I have fused quartz. And what we see is the refractive index, which is this number on this wall here, changes somewhat with, and again they've used wavelength here rather than frequency, but it's depends on the color. And so what we'll find is different colors will emerge from the prism, especially from the prism, because there's two incidents of refraction. There's refraction on the way in and refraction on the way out. So it doubles, if you like, the effect. we'll find red will give us a different angle of deviation compared with the blue or the violet, whatever. And so there is the breaking up of light into its colors, you know, red, orange, yellow, green, blue, indigo, violet. That's because of this dispersion. The angle of deviation is different for different colors. We get the angle of dispersion. The angle of dispersion is the angle between these two rays. How diverging is the red light from the blue light? That's your dispersion angle. So we have a deviation angle and we have a dispersion angle. Okay. Let's do an example of trying to find the angle of deviation. So this is a great time for me to check on your geometry. First of all, do you know what the definition of the angle of deviation is? And the angle of deviation is the angle between where the light would have gone and where the light did go. So there's my angle of deviation. That's what I want to find. Okay, so let's home in on this. I can find this angle if I can find that angle, and I can find that angle. Okay. So, I know this angle because that's a straight line, and that's a straight line. And in this case, I told you that that other one was 60, so that's 60 degrees. So this angle here, I can find this angle here if I know that angle there. Oh! If this is 150, then that's 30. Agreed? Because that has to be a straight line. Yep. If that's 30 and that's 30, then this angle here is 120. Agreed? Because that's a straight line. If that's 120, this angle here is 60, because that's a straight line. If that angle there is 60, this angle here is 60, because that's a triangle. 180 degrees to a triangle. This is a bad example in that it comes out to be an equilateral triangle, and they're not all equilateral. Okay, so just by coincidence that it's 60, 60, and 60. But that's how you do it. So it's not really, so there is a bit of optics there. You've got to know what the angle of deviation is, and you've got to know where it is on your diagram. But the rest is geometry. Okay? Newton got himself a nice big prism, and he put blinds up in his room, and he used a slither of sunlight. I find this hard to believe because I've lived in England. Not many days when you get a slither of sunlight coming into your room, but he lived in the picturesque south rather than the industrial north. So maybe I'm certain. Going back to what we talked about during the break, I grew up in a place where every old building was black, not because of using dark granite, but because they used sandstone and the soot covered it, made it black with coal dust. And I remember on certain school days not being able to see more than an arm's length in front of me and putting a scarf over my mouth and nose, just like we see from China now, and having little black holes where my nostrils were because I was breathing in the coal dust. And I was getting it was acting as a filter, very poor filter. I remember having bronchitis pretty well every winter, coughing up green phlegm. And generally that was nature. I didn't realize that it was different anywhere else, because I was in an industrial northern city with coal mines around and coal being burned everywhere. So my picture of Britain is, foggy, dank, dark, miserable days. It's much improved, in part because of, warming, which is depressing, although my brother cheers it, in part because of a lack of pollution. They stopped people from burning coal in houses. They stopped factories from burning coal and coke, and life got much better. So unfortunately, we are generationally the victim of our own success. My generation, if you talk about pollution, I take it really seriously because I've lived with it. But I understand when other people, they don't really get it because they've never really lived in a pollution-filled environment. But those pictures you see of Japan, of China, you know, are not that, I mean, it's more extreme, I think, than I had, but not by much, you know. So, yeah, so pollution's really bad. So, yes, in the south, not so much industry, so probably, and a lot before the Industrial Revolution, so probably very sunny during those days, maybe for all I know. People in, you know, Newton's time got suntans and all that kind of stuff. But he took this thing and he saw a rainbow of colours. And a solid, kind of, not solid, but a kind of overlapping colours. Red, orange, green, blue, indigo, violet. Red, orange, yellow, green, blue, indigo, violet. And we learned it as Richard of York gained battles in vain because he got killed at the end of it. And you learned it as Roy G. Biv. And my daughter learns it as red, orange, green, blue, purple. And I went berserk when I heard that. It was like, what's going on? And interesting thing was, I thought they were dumbing it down. And they are, but to some extent, when I looked at the spectrum, the colour spectrum, I need to put one up. I thought, well, you know, there's the red, and there's the orange, and there's the yellow, and there's the green, and there's the blue, and there's the indigo, and there's the violet. Forget this stuff at the end. And it's all equally spaced. But when you look at it, it's not. And the little bit of reading I did, what it turns out is that Newton believed there had to be 7 colours because a divine creator would use a divine number. Yeah.
He's really trying to find like puzzles in the Bible, man.
So it's like lucky 7. We're steeped in this kind of history. So when Copernicus thought, well, all planets must go in circles because it's a divine structure, then along comes Newton, and Newton saying must be 7 divisions because that's a divine number. This is one of the most intelligent people, and it's still seeped in it. It's so seeped in our culture. So it's just basically 7 somewhat arbitrary colours. When you have a situation, so where does this light come from? This light comes from atomic energy levels. So what happens is we have, say, any old atom. Hydrogen's the easiest one. And it has this bookcase of shelves. And imagine it kind of like that. And so if you put your electron on the bottom shelf, it has less energy than if you put it on the next shelf up. And everything wants to be on the bottom shelf, if it can. So you give this bit of energy by heating, it excites it up into the second or third shelf, and it sits there for an instant, and then it says, oh, I want to descend back, I want to relax back into my lower shelves. So it might go back in 2 steps. It might go back in 1 step, but in going back, it's got to give up energy. It can't have the wrong amount of energy to be on the shelf. And so in going back, it gives off a package of energy, which is the photon. And it gives off a very specific color of photon. And this one would have a different color of photon. And if we did this all in 1 step, that would have an even different color of photon. This double jump would be bluer than these other 2 because it has more energy in it. Maybe these are of energies that we cannot see. There's no guarantee it's going to be visible light. Maybe it will be ultraviolet or maybe infrared. We can't see it, but the more energy, the higher the frequency of the light. Okay. So when I get a gas and I excite it, I see lines of color. because all the hydrogen atoms can have that transition from one energy level to another, and they can have that transition, and they can have that transition and these transitions, but you can't have one in between because there's no energy levels in between. So all the atoms behave the same, and they give you these very distinctive lines of color. Now, when you look at a hydrogen source, you don't see lines of color. You see a dominant color, probably a bluey, greeny red. You see them all superimposed on one another, but it's a very distinct color. And if I was to take helium, because it's a different atom structure, I would get a different array of visible lines. And if I had sodium, I'd get different visible lines. And if I had mercury, different visible lines. So ironically, from a chemistry point of view, this is amazing because I can look at the light emitted by a source and I can tell you what the species is that's been excited. Newton didn't see that. Newton saw a rainbow of colors, but he saw the rainbow. He saw all the possible physical colors that our eyes can see. And what's going on there is the sun's surface, which is emitting the visible light, is denser than this gas inside these tubes. And when the material is denser, it means that the atoms are actually bouncing into each other. Basically, in these gas tubes, it's very unusual for the atoms to bounce into each other. Basically, they bounce into the walls of the container. So they don't know about these other gas atoms. When the atoms bounce into each other, we have basically the Pauli exclusion principle, which says no two atoms that are bouncing into each other can have the same energy. So what they do is they start splitting their energy levels. Let's say there's 3 energy levels, but there's 1,000,000 atoms bouncing into each other. So the first one has that, and the second one might have that, and the third one might have that, and the fourth one, I'm going to keep them in order. So you get this array of energy levels, and this array of energy levels, and this array of energy levels, and they all overlap. And so what we get is we get a continual distribution of colors. So when you get a rainbow, you're looking at something that's denser than when you get these lines. But the principle's the same. And so Newton looked at these rainbows and he named them and he broke light up into different colors, and he did some very interesting experiments. He took sunlight and broke it up into its colors, and then what he did was he took another prism and recombined the sunlight. Doing that the backwards way around. He recombined and got white light. It wasn't clear to him whether the sunlight was knocking the colors out of the glass or whether the sunlight contained the colors. All he knew here was, well, I create all these colors, but then I can recombine them. He took an experiment where he took red light. So he took a prism and he got red light out. And then he put the red light through a prism and he couldn't break it up into any more colors. So bit by bit, he reckoned that the sunlight contained all the colors. So sunlight is white light and it contains all these colors. And the colors were indivisible. Once you got down to the basic thing, it was indivisible. There wasn't like, unlike with pigments. Well, no, that's not true again. I got to be careful now. If I take a color, well, I got to be careful now. I can combine different colors and make white light. I can combine other colors and get other colors. You know, I can get red light and orange light and get another color. Okay. But there's not colors beneath the colors that we see. So people said, well, this is a very useful machine. Why don't we just take this glass prism and we have a source of light, maybe a flame, and put a salt into the flame, and we have some kind of defining aperture so that we don't see just the flame, we see a slit of light. And then we have a telescope or a microscope, depending on what you want to call it. And we can actually plot out these lines. We can have peak and peak and peak and peak and peak and peak. And I can measure the angle between these things. And from the angle, I can do some calculations. I can measure the energy levels. And this is quantization of an atom. The fact that there are allowed energy levels and not allowed energy levels is quantization. You either have or you don't have. It's kind of interesting. And back in the day when I was a student, we used something like this. And we would look at all the individual lines for hydrogen, and we'd get the angles, and we'd do the calculation, and we'd figure out what the energy levels of hydrogen were. And when they started doing astronomy, they basically were a bit cleverer. What they'd do is they'd put a prism here and they'd put a glass plate here, and they'd get the lines from stars. And then they'd look at the spacing of the lines on a photographic film. And think about it. A star is so weak in intensity. How long do you think you have to sit there before you get a measurable signal on your glass plate? There's basically Hubble. Hubble was kind of like a very famous scientist of his day. He was a well-to-do American who went to Britain to do research. Came back with a British accent, which either pleased people or upset people. Basically got a job at the Wilson Observatory, I think it was, just outside Los Angeles. So he could have the dual life. He could be the scientist, and he could also be the socialite. So he was him and his wife were very well known. They knew Hollywood people. They were very well known. And he would go off to his mountaintop and do his research. Well, he had an assistant. And Hubble was interested in these things called nebula, which were like fuzzy stars that he had a 100-inch telescope, which was the biggest in the world, so he could see fainter objects than anybody else. And he could see these faint objects better than anybody else. And there was a question of what were they? Where were they? And the like. And so his assistant did an awful lot of spectroscopy on nebula. And that involved night after night after night, going back and putting the same photographic plate in the same position and tracking the same nebula so that hour upon hour of data collection built up until he could get the spectral lines for that nebula. And then he'd compare it with a neon tube or a hydrogen tube or whatever in his lab. And they did a very interesting thing. Not only did they see that it was mainly hydrogen, which is what you see pretty well all over the place, but what they saw was the hydrogen was in the wrong position. It was hydrogen, the fingerprint was there, the pattern was there, but it was, redder than it should have been, and so on. And they were able to figure out, I think I'm joining people together here, but, forgive me on that. But basically, they were able at that time to figure out that these things were not only way, way, way beyond the edges of what we thought of as our universe, but they were traveling away from us at a fantastic speed. And so very quickly we got the idea of the island universe. We have a galaxy, and there's these other galaxies out there. Everything we see in our galaxy is repeated in this nebula, but the nebula is speeding away from us. And I can't tell you, astronomy is a fascinating field, and it's pretty well all done with light. And what we understand about our universe based on the photons that reach us and how we interpret the photons is it's phenomenal, the information we get. It's phenomenal thing. These days, you don't need to use a spectrometer like that. You use one of these things. We have one in the lab. It's an ocean optics spectrometer. The light comes in, we reflect it a few times, we refract it, probably diffract it actually, and we get it going onto not a photographic film, but an electronic array of pixels like in a digital camera, and we get a spectrum already done for us. And so we can just look, and the computer will tell us, oh, that's hydrogen, that's helium. It's just the principle is the same. The technology is improved because of materials, basically. So we can have the helium spectrum, and we can have all this stuff. We can figure it out. Let's say we go swimming. Let's say we go to the aquarium and we go inside that, swimmer for the day where they let you swim with the sharks. And you look at all those people in the observation gallery. Anybody not been to the aquarium? Good, okay. And what you will see is a circle, and like all the people in like a fisheye lens, and then you'll see reflected mirror of the fishes around. You will not see a wall of glass. If you're on the other side, you'll see just the fish tank. But you will get this total internal reflection around here. What's going on is this. I've drawn the arrows in just this way. Imagine shining a light out of the water into the air. If it strikes the interface at 90 degrees, there's no refraction. As you go to a less dense medium, you are refracted away from the surface normal. So at some point, the refracted ray runs into the surface of the water. And this is called, a critical angle. If you go beyond the critical angle, so there's the critical angle. If you go beyond the critical angle, you get total internal reflection, which is better than a mirror. It's better than using a silvered or a aluminized surface. It's better. So in fancy optics, if you want to reflect something, you use a glass prism. You don't use, or use a quartz prism, you don't use a little mirror. Cheap optics, you'd use a little mirror, and it won't last very long. Expensive optics, you'll use a prism. Now, the book goes on, and I want you to know what critical angle is. And the critical angle is the angle of incidence that gives you a refracted ray that goes along the surface. And it has a special equation for it. But this is just Snell's law, with that equal to 90 degrees. So don't learn a special equation from it. Just learn that the critical angle is the angle you need in the low refractive index in the high refractive index material to give you a 90-degree angle of refraction in the low refractive index material. And remember this example, water and air, and you won't get it backwards. And that once you get bigger than the critical angle, you get total internal reflection. I want to jump a slide. Total internal reflection is incredibly useful. It's not just going to the aquarium and seeing a fisheye lens. I don't know where I drew it. And seeing a fisheye lens somewhere. Seeing a fisheye lens. That's a trivial example. Communications uses total internal reflection. I send a laser light down an optical fiber, glass fiber typically. And if I send it in at a big enough critical angle, beyond my critical angle, I don't get light refracted, I get total internal reflection. So all my signal stays inside the wire, and stays inside the wire, and stays inside the wire, and stays inside the wire. This is better than having an electrical signal. First of all, it's not influenced by electric fields. And secondly, I can chop into ones and zeros a light source much better than can chop because of induction an electrical signal, yeah. The inductance is going to fight you in an electrical signal. If you try and turn something on and turn something on off instantly, it's going to be a real pain. But I can turn light on and turn light off much better. And I can use different colors. Hey, let's look at orange light. Let's put a filter on. I'm only going to look at the orange signal. Let's look at green light. I'm only going to look at the green signal. So one fiber optics can carry way more information. I distinctly remember when on the news they had music that was being produced in California, played in Denver, I think it was, over the internet. And they said this was phenomenal because having a signal sent, that complex a signal sent over wires was just a phenomenal feat. You can send radio waves, but you couldn't send a signal down wires. And now we have video all over the place. I mean, not just music, but video. And that's because of the influx of fiber optics. It's basically meant such a huge difference. I recently had fiber optics repaired to my house. It got broken. We had it repaired. Actually, no, we went up from standard FiOS to super zillion FiOS and all that kind of stuff. And the guys who came to put it in were like, I told them I was a teacher, so they showed me some of the cables. And the cable is basically, I was very impressed with it. The cable's like, it's got wire thing, well, not wire things in, but hard plastic things in, so you can't bend it too much. Because here's the problem. If I bend this too much, then what happens is that what was beyond the critical angle here is not beyond the critical angle, so I end up with leakage. So, and it's a tiny slither of a wire. It's basically, you can hardly see it. The actual fiber optic is tiny. And all the rest is protection for it. And they have a special machine that when you basically bond two pieces of fiber optic cable together, there's a special machine with little microscopes inside that bond, so you can line the thing up perfectly and bond the two pieces of wire together, two pieces of glass fiber together. The whole technology there. And those guys, I talked to those guys, and they didn't necessarily know the science language, but they knew what they were doing. It was very interesting, that whole thing about how do you train people to do things. You explain it in a way which is accessible. You don't have to start off teaching them all about light. So I remember saying to the guy, oh, I guess you can use a lot of different colors. And he goes, oh no, we use bands. And there's like 2 or 3 bands. And I'm going, yeah, it's 2 or 3 colors. And he's going, no, they're bands. And it was very clear to him I had to call them bands, because that's what he'd learned. But it's colors of light that he was looking at. If you change the difference in the refractive index between these two, then you change the critical angle. So one of the reasons why this is so protected is if it was just open fiber, like this is a piece of plastic. It's a bit of an extreme case. Now, I'm not near the critical angle here, but if I was to put oil or grease on here rather than air, I would change the critical angle, and so I could get refraction rather than reflection. So you've got to be careful about that. And there's a guy, Dick Dew at USF, who works on graded optical fibers, so that rather than having a hard interface between the optical fiber and the outside world, he has a graded interface, so he can change the refractive index so the actual light doesn't actually get to the surface. It gets near the surface. He's worked on that for years. And that's a way of doing it. So this is huge technology. So a light pipe can be constructed from a glass fiber. Light is totally internally reflected when it strikes the side of the tube. Optical fibers can be very efficient, transferring virtually 100% of light from one end of the fiber to the other. Light pipes are used in telecommunications, medical imaging, I had a endoscopy done recently, and the doctor just put a tube up my nose and down, and I could kind of feel it, something at the back. I thought, oh man, I must have some mucus because I can kind of feel stuff falling down my throat. And the doctor says, no polyps on the vocal folds. So the optical fiber was looking down here, had gone through my nasal cavity. And it was like, try that 5 years ago. That would have been a bit more painful. Light pipes are used in telecommunications, medical imaging, and many other industries. But that's not to say, I mean, this is done with water. This is a light pipe made of water coming out of a 2-litre bottle of drinking fluid. Which ray is totally internally reflected would be E. Which light ray depends the critical angle? It's 4 is the critical angle. Let me just do this one example because it's the last thing I really want to talk about. So we say determine the critical angle of the interference between that. So basically I say N1 sine theta 1 equals N2 sine theta 2. So I got 1.2 sine, that's going to be 90 degrees, is equal to 1.7 sine theta c. So I'm going to say sine theta c is equal to 1.2 sine 90 over 1.7. Sine 90, last time I checked it was 1. That's 1.2 over 1.7. So I can say second sine of 1.2 divided by 1.7. I'm getting 44.9 degrees. Theta c equals 44.9 degrees. So there we have it. Pretty straightforward.
So your sine 90 is always on the lower end value?
You don't get, so if